Welcome to our video series. We will love to hear your ideas for future videos. Now, let's dive into the topic of the Silicon Cambrian explosion. In this page, we will cover the fundamental shift from traditional hard-coded logic to the creation of evolutionary environments in the age of artificial intelligence. For decades, computer science was defined by rigid rules and deterministic algorithms where every outcome was predefined by a human programmer. However, we have entered a period of rapid diversification and growth, similar to the biological Cambrian explosion. Instead of writing lines of static code, we are now designing digital ecosystems that can grow, learn, and adapt. This page sets the stage for understanding how advanced data structures and algorithms have evolved to meet the demands of modern compute. We will look under the hood of these complex systems to see how they differ from the software of the past. Forget what you know about traditional programming, because we are no longer just writing rules. We are building environments where intelligence can emerge through massive data processing and architectural innovation. This transformation marks a new era in technology where the software evolves based on the data it encounters rather than being confined by its initial design. Let us begin our exploration of this exciting new landscape. In this section, we discuss backpropagation and the first mutation. This concept represents the moment digital logic began to rewrite itself. At its core, backpropagation uses chain rule calculus to directly update weight matrices based on the gradients of error. This is essentially digital DNA modifying its own structure to improve performance. For 60 years, the industry built static and soft-bodied logic trees that were brittle and difficult to scale. Backpropagation changed the game by introducing an algorithm that writes its own data structures based on its mistakes. We see the mathematical representation where the change in weights is proportional to the negative gradient of the error. However, this process faces a challenge known as the order n-squared trap, where the complexity grows rapidly with the size of the network. The visual layout shows how the input layer, hidden layer, and output layer interact through activation functions and weight updates. By calculating the partial derivatives across the network, the system can pinpoint exactly where an error occurred and adjust the weights to minimize future failures. This self-correcting mechanism is the foundation of all modern deep learning, allowing machines to find patterns in data that are far too complex for human programmers to map out manually. Our third topic highlights that compute is the environment. One of the most important lessons in modern AI is that you should never design an algorithm without understanding the hardware it lives on. In 2012, AlexNet achieved a historic breakthrough by dropping the ImageNet error rate to 15.3%. This success was not just about the math. It was because the parallel geometry of the algorithm was perfectly suited for the GPU ecosystem. We see a visual comparison where traditional sequential code is crossed out in favor of massive parallel blocks that utilize the hardware of an NVIDIA GPU. This slide serves as a warning that if your code cannot parallelize across a GPU array, it will essentially go extinct. You must adapt to the physics of the hardware, or your ideas will fail to gain traction. The architecture of the chip determines what kind of intelligence can survive and thrive. When we design for the modern era, we are not just thinking about logic, we are thinking about the thousands of tiny cores that process data simultaneously. This hardware-centric approach is what allowed deep learning to move from a theoretical concept to a world-changing technology that dominates our current digital landscape. Next, we examine the transformer phylum, which we describe as a vertebrate architecture. This is the apex predator of our current technological ecosystem. The transformer has become the dominant architecture because its skeletal structure parallelizes perfectly, allowing it to scale from 117 million to over a trillion parameters. The core innovation here is the self-attention mechanism, which utilizes three main components known as query, key, and value matrices. Unlike previous models that process data in chunks or sequences, the transformer processes entire sequences simultaneously. This provides a form of lossless memory across the full context window, allowing the model to understand the relationship between words or data points regardless of how far apart they are in the sequence. The visual shows how the input data is projected into these different spaces to calculate attention scores. This ability to handle massive amounts of context with perfect parallelization is why transformers have taken over the fields of natural language processing and beyond. They represent a significant evolutionary step forward in how we structure data for machine learning, providing a robust framework that can support the massive scale of modern artificial intelligence models. While transformers are powerful, they come with a significant cost known as the key-value cache memory trap. In this page, we explore how memory usage scales at order n squared. This means that as you increase the length of the sequence the model is looking at, the memory requirements grow quadratically. Every single token in a sequence must attend to every historical token that came before it, and the key-value cache must store all of this information to remain efficient. The graph illustrates this dramatic curve where memory usage spikes upward as the sequence length increases. This is a trap that many developers do not encounter in introductory courses, but it becomes a major bottleneck in production. If you double your context window, you effectively quadruple your memory cost. Without careful management, this unchecked growth will eventually obliterate your compute budget. This slide warns us that while infinite context sounds like a dream, the physical reality of hardware memory limits makes it a difficult challenge to overcome. Engineers must find clever ways to manage this cache or risk creating models that are too expensive to run at scale. Understanding this limitation is vital for anyone looking to deploy large language models in real-world applications. Moving into the realm of image generation, we look at diffusion and the evolution of imagination. While transformers are designed to predict the next token in a sequence, diffusion models are built to imagine entirely new data. This is a completely different biological branch of the AI tree that solves generative problems through the concept of reversed entropy. The process begins with evolutionary generation via statistical physics. We take a clear image and slowly add destructive noise until it becomes a meaningless cloud of pixels. The model then learns the underlying data distribution by attempting to reverse this process. It starts with pure noise and gradually removes it to reveal a coherent image, such as the spaceship shown in the diagram. This denoising process allows the model to create highly detailed and realistic data that it has never seen before. It is not just copying, it is synthesizing new information based on the patterns it learned during the noise reversal training. This marks a shift from simple prediction to true creation, where the machine uses statistical principles to generate complex visuals from nothing. It is a testament to how different architectural choices can lead to entirely different capabilities within the same ecosystem. Despite their creative power, we must address the latency bottleneck in diffusion. While the results are often beautiful, the process is computationally agonizing at inference time. The visual comparison between path A for a transformer and path B for diffusion illustrates the problem clearly. High-fidelity denoising requires dozens or even hundreds of sequential network passes to generate a single output image. This leads to severe inference latency, as the system must step through the noise reversal process one iteration at a time. In contrast, a single pass through a transformer is much faster. This slide reminds us that in the world of engineering, you almost always trade speed for quality. When you are building a system for a specific use case, you must know your service level agreement before choosing this architecture. If your application requires instant results, a traditional diffusion model might not be the right choice unless you have massive compute resources or have optimized the sampling steps. Navigating this bottleneck is a key part of modern AI deployment, as developers seek to balance the desire for high-quality generated content with the need for responsive and efficient user experiences in real-time environments. Now we turn our attention to Mamba and the mammalian memory shift. This architecture represents the genetic mutation we have been waiting for to solve the scaling issues of transformers. Mamba utilizes selective state spaces to maintain a compressed summary of the context that updates continuously. Unlike the transformer, which stores everything in a massive key-value cache, Mamba selectively forgets the garbage and remembers only what truly matters. This allows the model to achieve linear time scaling, meaning the complexity grows at order n rather than order n squared. The visual shows the difference between the bulky, failure-prone quadratic growth of the cache and the sleek, efficient hidden state of the Mamba architecture. For long sequences, inference can be approximately 5 times faster than traditional methods. Mamba offers the promise of infinite context at a linear cost, which is a massive leap forward for processing long documents or complex data streams. It functions much more like a biological brain, filtering through information and keeping only the relevant parts in its working memory. This shift could represent a new lineage of models that are better suited for the long-term reasoning and efficiency required by next-generation applications. Every innovation has its downside, and here we explore the trade-off of compressed state retrieval. Because the state in models like Mamba is selectively compressed, the exact retrieval of a specific fact from deep context can fail. This is in contrast to the expensive but perfect recall offered by a transformer. The visual shows a long data block where a specific hyper-granular data node is being targeted. However, the compression process is lossy, leading to information degradation on exact recall tasks. If your application requires perfect needle-in-a-haystack performance, where every single detail must be retrieved with absolute precision, Mamba might drop the ball. It is a classic engineering trade-off between efficiency and accuracy. You gain massive speed and memory benefits, but you lose the guarantee that every single bit of information is perfectly preserved. This page reminds us that there is no one-size-fits-all solution in AI architecture. You must pick your trade-offs based on the specific needs of your project. If you are summarizing a book, lossy compression is fine. If you are retrieving a specific password from a 1,000-page document, you might need the more expensive and heavy architecture of a transformer. We now look at convergent evolution via sparse activation through the mixture of experts, or MOE. This is a fascinating phenomenon where different organizations like Google, OpenAI, and Mistral all landed on the same architectural solution independently. When the hardware constraints are identical, nature often invents the same wing over and over. The mixture of experts approach routes the input to specialized subnetworks, activating only a small portion of the total model for any given task. This effectively decouples the theoretical parameter capacity from the active compute or floating point operations. The visual depicts a central router directing data to specific expert blocks that are optimized for different types of information. This allows models to have a massive total size while remaining relatively fast and efficient to run. It is a form of sparse activation that mimics how different parts of the brain specialize in different functions. By only using the parts of the model that are necessary, we can scale intelligence further without hitting a wall of computational impossibility. This convergence toward MOE architectures shows that we are uncovering fundamental truths about how to build large-scale intelligent systems within the limits of our current hardware. Next, we discuss flash attention as a hardware hack. This is not a new model or a new way of thinking about intelligence. Instead, it is an algorithm that was rewritten specifically to respect physical hardware limits. In modern GPUs, there is a massive bottleneck between the fast SRAM cache and the high bandwidth memory, or HBM. Traditional attention mechanisms involve too many read and write operations, which slows down the entire system. Flash attention fuses these operations to keep data entirely within the fast SRAM cache as much as possible, bypassing the massive memory bottlenecks. The diagram shows the traditional paths crossed out in favor of a more direct and efficient cycle. As the slide states, if you are not using this, you are essentially burning money. It highlights the importance of hardware-aware programming in the age of AI. Sometimes the biggest leaps in performance do not come from a new mathematical formula, but from a better way of moving bits around on a silicon chip. This optimization has become a standard in the industry, enabling larger models and longer context windows by simply being smarter about how we utilize the memory hierarchy of the hardware. We must also consider the fragility of the transformer monoculture and what is known as the Habsburg trap of over-optimization. We have bred an entire ecosystem where every major artificial intelligence is a variant of the transformer. This extreme efficiency in the current GPU environment leads to extreme fragility if a paradigm shift occurs. The visual shows a massive array of identical transformer blocks being split by a sudden crack representing neuromorphic chips or a hardware shift. If quantum or optical chips take over tomorrow, these models could become obsolete overnight. We have optimized so heavily for the current silicon architecture that we might be ill-prepared for the next leap in computing technology. This slide is a call to stay adaptable and to continue exploring alternative architectures. While transformers are currently the dominant species, the history of biology and technology shows that dominant species often struggle to adapt when their environment changes. As researchers and engineers, we must keep an eye on the horizon and be ready to pivot if the underlying physics of our compute environment changes. Diversity in architecture is not just a theoretical goal. It is a survival strategy for the future of intelligence. In the world of model training, we see horizontal gene transfer and model collapse. This refers to distillation and the use of synthetic data. We are increasingly training small models on the outputs of massive models to bootstrap their capabilities cheaply. This is shown as a teacher model passing information through a pipe to a student model. However, this process acts like a digital virus. Errors, biases, and hallucinations present in the teacher are amplified in the student because there is no real-world grounding to correct them. It creates a feedback loop of garbage in and amplified garbage out. While this technique allows us to get capabilities fast and at a lower cost, it risks a collapse in the quality of the models over generations. As the student learns from the synthetic data of the teacher, the nuances and truths of the original data distribution can be lost. This page warns us that relying too heavily on models talking to other models can lead to a degradation of intelligence. We must ensure that our models remain grounded in high-quality human data and real-world observations to prevent this cycle of decay from ruining our digital ecosystem. As we move forward, we are seeing synthetic speciation for new environments. We are no longer just building chatbots. We are engineering specific lineages for specific niches. We are shifting from passive stimulus response APIs to goal-directed, autonomous agents that can manage long-term state. The visual shows a central transformer branching out into specialized areas like edge AI, multimodal systems, and agentic state management. Edge AI requires small, efficient models for local hardware, while multimodal models must handle images, sound, and text simultaneously. Agentic systems represent the next big leap, where the AI is not just answering a question, but taking actions in the real world to achieve a goal. You are not just building functions anymore, you are building entities. This speciation allows AI to inhabit different parts of our lives, from our phones and cars to our workflows and personal assistants. Each niche requires a different set of optimizations and architectural choices, leading to a diverse family of models that each excel in their own domain. This evolution reflects the growing complexity of our needs and the incredible flexibility of the underlying technology. In our final page, we conclude with the idea that you are the natural selector. The fitness criteria for the next form of intelligence are determined entirely by your architecture choices, your reward signals, and your deployment constraints. For 4 billion years, biological evolution was a blind process. Now, the evolution of intelligence is being directed by the code you commit. This is a massive responsibility for every developer and researcher in the field. The decisions we make today about how we structure our data and our algorithms will shape the capabilities of the systems that define our future. Don't write garbage because the ecosystem will reflect the quality of its components. We have the tools to build incredible things, but we must be intentional and thoughtful about our designs. This brings us to the end of this video. We hope you found it informative and engaging. If you have any questions or suggestions, please leave them in the comments below. Don't forget to like, share, and subscribe for more content like this. See you in the next video.